So I think, at least for the next several sections, I think things are going to get a little bit easier for us because we're going to move away from the theoretical. We're going to get into some of the shortcuts for doing some of the things that we've had no good short way to do things. It'll be a lot more symbol pushing, where it's going to feel like, like an algebra kind of math course for a little bit. So feel a little bit more comfortable. And, like how Mr. Kulik told you, like, hey, that's a derivative you should be able to do in your head. Like, not right now, but pretty soon. We're going to start building out the rules for, like, how to do some of these shortcuts. So a lot of these derivatives are going to become like mental math problems that would have been like, that's a whole sheet of paper when using the definition, which is lovely, right? I'm super excited too. So these first few sections of chapter 3, I think the first 3 or 4 are all going to be just on these shortcuts, or like how to do more complicated or how to deal with like combinations of these shortcuts. So this first section, we're just going to be talking about derivatives of polynomials and exponential functions. So we're just going to see a whole bunch of theorems here on how to do the derivatives. So the derivative of a constant is 0. Let's prove that. How would we prove this? The definition of a derivative. So if f of x is just equal to c, what's f of x plus h equal to? C. And what's f of x? C. C minus c is 0. 0 over h is 0. And then the limit of a constant is just the constant. Proof done. Yay! But now this becomes, instead of like, a big whole line of text, it's literally mental math, right? Derivative constant 0. Done. The derivative of x is 1. Okay, well, let's prove that. How are we going to prove it? The definition of a derivative. You guys sensing a pattern here? No? And then h over h is just 1, and the limit of a constant is a constant. And we're done again. So far, so good? Nothing shocking yet. I think some of us have already read ahead or talked to somebody who knows something about the calculus and had figured this out. So this is called the power rule. So the derivative of x to the n is just n times x to the n minus 1. You move the exponent to the coefficient and subtract 1 from the exponent. And that works for all values of n. So whether n's a fraction or decimal or a negative number, whatever. It'll all work. How would we prove this? Here's a shocker for you. We're going to use the definition of the derivative. Oh my goodness, Mr. Kulik. You're kidding me, right? Nope. Now this one's a little bit yucky. Why is this going to get kind of yucky? Because of this piece right here. What's going on right there? Now I guess for this proof, we're going to assume that the n is a positive whole number. Because what I'm going to use right now is the binomial expansion formula, which is a deep pull from Algebra 2. Do you remember the binomial expansion formula? So it's going to give me x to the n plus n, well, it's really n choose 0, then n choose 1, x to the n minus 1, h to the first, plus n choose 2, x to the n minus 2, h to the 2, all the way down to n choose n minus 1, x to the first, h to the n minus 1, plus n choose n, h to the n. N choose 0 is 1, and n choose n is also 1. So those guys can just cancel out. I'll notice that now everything that remains has a factor of h in it. So they can all cancel out. So and now everything drops off when I do the substitution that has an h in it. So I'm left with just n choose 1, x to the n minus 1, and n choose 1 is just n. And we're done. Just FYI, would Mr. Kulik ever ask you to repeat one of these proofs on a test? Yeah, probably not, right? Okay, let's do a couple of practices here just to make sure we got it. What's the derivative of x to the 6th? 6x to the 5th. Good job. How about y equals x to the 1,000? Yeah, let's actually include some notation here. Do it that way. And you said 1,000 x to the 999. Great. about y equals t to the fourth? I'd probably call that dy dt equals 4t to the third. Yeah. All right. F of x equals 1 over x squared. Yeah, so you want to think about that as the same thing as x to the negative 2. So then you can do negative 2x to the negative third, or negative 2 over x cubed. This trick of like taking something that doesn't exactly fit the shortcut and rewriting it so you can use the shortcut will be like a foundational skill for the next like 3 or 4 chapters. Is a lot of calculus becomes, what kind of algebra manipulation can I do to this thing so I don't have to do like heavier calculus. It's going to be very much a pattern of work smarter, not harder. What kind of sneaky crap can Mr. Kulik pull from Algebra 2 to make this problem easy? We'll do one more of these examples and then we'll move on. How about y equals the cube root of x? Yeah, we can think about that as x to the 1/3. Or we could just write that as 1 over 3x. And then maybe because 1/3 minus 1 is negative 2/3. What do you think about that? Cool, right? Like these are derivatives that are like really kind of a pain. I mean, we saw one very similar to this on the test where you're asking to find the derivative using the definition. That turned into like a pretty incredible hassle. And that we did it in our head. Oh, yeah. That's what I'm talking about. All right. Couple of definitions and then a handful more theorems, and then we're try to get it in and out of here. So we talked about tangent lines to a curve, right? There's another kind of line that we call the normal line. So a normal line to a curve C at the point P is the line through P that is perpendicular to the tangent line at P. So just to kind of visualize things, let's say that's our P. So that's like our tangent. So like this would be what our normal looks like. Everybody's cool? Visualizing what it is that the normal line is? Let's do a quick example of finding one and writing the equation. So let's say we want to find the equation for the normal line to the curve y equals x times the square root of x at the point 1, 1. Okay, in order to write the equation for a line, what do I need? I need slope, and I need a point, right? What's the point? 1, 1. They gave it to me already. How am I going to find the slope? I'm going to use the derivative to figure out the slope of the tangent line. And then if you remember all the way back to Algebra 1, what's the relationship between two lines that are perpendicular? Their slopes are negative reciprocals. Okay? So I'm going to need like 1 over dy dx at x equals 1. Oops, negative 1. Everybody's cool with that? That's just me writing some notation about how I'm going to do these things. All right, so let's find the derivative of y equals x root x. First thing I'm going to do, the way it's currently written, x root x, can I take the derivative of that? Nope, not the way it's currently written. But that's really the same thing as x to the first times x to the 1/2, or x to the 3 over 2. And that I can take the derivative of. You like that sneaky trick there? So what's the derivative of x to the 3 over 2? 3 over 2 x to the 1/2. And if I want to evaluate that at x equals 1, what do I get? Square root of 1 is 1 times 3 over 2 is 3 over 2. So the slope for my normal is going to be negative 2/3. Everybody's cool with that? Okay. So now I got everything I need. So I'm going to use the point slope equation for a line. Y minus y1 equals m times x minus x1. So I get y equals negative 2/3 x, and then I get plus 5/3. Mackenzie. This right here, that's just me writing the slope, the negative reciprocal of the slope of the tangent line at x equals 1. So like when I put this vertical bar here, and then I write the value of x in the subscript, that's just saying that I'm plugging x equals 1 into that derivative equation, whatever that equation is. Is that what was confusing? Was the notation? How I got to this? Gotta do this. You're talking so quiet, I'm having trouble hearing you over people next door. Okay, try again, Mackenzie. I couldn't hear you. Of 3 over 2? Oh, I just took that's the negative reciprocal of the slope of the tangent line, right?
Why is it the negative reciprocal?
That's how the two lines that are perpendicular, their slopes are negative reciprocals. The normal is perpendicular to the tangent line. So I found the slope of the tangent line. That was the 3/2. And then took the negative reciprocal to get the slope for my normal line.
So you found the tangent line by the first of it, of the function.
Yeah.
You found the normal line by doing the inverse.
The negative reciprocal. Yep. Taylor.
Can you walk me through how you got to the x? It's like the 3/2x and then the 1/2. Like that part?
Yeah. So from Algebra 2, I remember this identity, right? So a square root has an index 2. We never write the index 2 there. Stop talking, please. But I know it's there. So that's how I did that. And then I remember from Algebra 2, x to the a times x to the b is x to the a plus b. So x to the first times x to the 1/2 is x to the 1 plus 1/2, which is 3/2.
Okay. All right. Thank you.
Uh-huh. Mackenzie, I don't feel like I really answered your question. I know Mia was talking to you. Did you guys got it squared away?
Yeah.
Are you sure? I feel like I failed.
No, it's fine.
Okay. All right. Here we go. Some more theorem time now. Here's one that's super helpful. Assuming that c is just some real number and f is differentiable, then the derivative of c times f of x is just c times the derivative of f of x. I'm going to skip the proof here in the interest of time. So if f and g are differentiable, then the derivative of f of x plus or minus g of x is just going to be the derivative of f of x plus or minus the derivative of g of x. So what are these two theorems here saying in conjunction? That if I'm taking a derivative, I can just ignore the constant. I can just pull the constant out front and take the derivative of the variable part. And if I have the sum or difference of a bunch of functions, I can just take the derivative one at a time. Basically, the derivative distributes throughout my function to the terms, right? So let's say we got something like this. Ay caramba, Mr. Kulik. What's going on here? I guess I should have said the derivative here because my notations aren't matching. Okay. So I'll say dy dx is equal to d dx of right? We'll just take the derivative of both sides. Everybody's okay with that idea? And then using the previous two theorems, I can distribute that derivative to each term. And on each term, I can pull the constant out to the front. Victoria? I'm just showing you how I'm using the two theorems. This is entirely a mental math problem still.
Okay.
But I wanted to, before I do the mental math, since these are notes, I want to show you like what I'm doing internally. Does that make sense?
Yeah.
So again, you would not have to write this all out. I'm just showing you like what's happening in my head when I'm doing it.
Right.
But this is entirely a mental math problem. Is everybody okay with kind of what I did there? Again, I'm just writing out all the work here. This is something that reasonably you would just elect to do in your head. Maybe not right away, but by the end of the homework for this section, this would be something that you'd want to feel comfortable that you could do in your head. But again, what I did was I used the two theorems to distribute the derivative to each term. And then on each term, I pulled the constant out front of the derivative. And then I took the derivative, multiplied the constants back in, and added things to, or combined any like terms that might have been created. And that's it. It's not bad, right? Think about how bad that would have been to do by hand with the definition with the 8th, 5th, and 4th degrees in there. Like, oh my goodness. That's like, I'd have to turn my paper landscape and still it's going to run onto like multiple lines on me. Like, what a nightmare. This you could do in your head. Whoa! That's pretty nice. Okay, let's say I want to find the points where f prime of x is equal to 0. What are these points where f prime of x is equal to 0 equivalent to? Assuming that I have a continuous function. They're extrema, right? The place where the derivative is equal to 0 is going to be at like a maximum or minimum. Or possibly like something like this where it goes and it flattens out and then it goes up. Okay. So what's the derivative of f going to be? That look good to you guys? Okay. So I'll set that equal to 0 then. How do I solve something like this? You don't need your calculator. I would factor out a greatest common factor of 4x. Okay, that looks good. Then what? Great. Apply the zero product property to set each term equal to 0. So when I divide by 0, I get, or divide by 4, I get 0. If I add 3 to the both sides and then square root both sides, I get plus or minus the square root of 3. So those are the x values when the derivative is 0. But if I want the points, I should get a y coordinate also, correct? Where should I be plugging the x's into? F or f prime? To the function or the derivative? The function. If I want the points where the derivative is 0, I'm plugging the x's back into the function to find the extrema, right? Everybody's okay with that? This becomes one of the trickiest parts for students, is just making sure that they're plugging things back into the right places. So if I do f of 0, I get 4. So that means that we have some kind of extrema at 0, 4. If I plug in the square root of 3, that's going to give me 9 minus 6 times 3, so 18 plus 4. So that gives me negative 5. So we have the square root 3 comma negative 5. And if I do the same thing at negative root 3, I get the same y coordinate. Is that a problem? No, man. That's fine. So if I'm looking for the points where the derivative is 0, those are the 3 points where the derivative is 0. What do you guys think?
Side where you did x open parentheses x squared minus 3.
I just set the pieces equal to 0 and solved. I applied the zero product property like I'd solve any other polynomial.
Right. Okay. And
I took those values of x's and plugged them back into f to find the y coordinate.
I mean, like, why'd you split it?
Because if I have 2 things that multiply to give me 0, one of the 2 or both of them have to equal 0,
Okay, I see.
right?
Yep.
That's the zero product property.
Okay.
Okay. Let's talk a little, that's been all about polynomials. Let's talk now about some exponential stuff. So let's suppose f of x is equal to a to the x. Let's say we want to find the derivative of this. Since we don't have a rule specific for an exponential function, why is this exponential? Or how can I look at it and tell this is an exponential function, a to the x? The x is in the exponent, the variable's in the exponent, exactly right. Oops. Ugh. Forgot the limit. Okay. What am I going to do with this? Algebra 2 time here, folks. Watch this trick. A to the x plus h is the same thing as a to the x times a to the h. No natural logs. That's a bad idea. Everybody's cool with why that is? A to the x plus h is the same thing as a to the x times a to the h, right? That's just your power properties from algebra. Now I notice that I have a greatest common factor of a to the x that I can factor out. Everybody's cool there? Notice that the limit that I'm taking is as h approaches infinity. My a to the x doesn't contain an h in it. So I can really just kind of pull that out front. I'm sorry, 0. Did I say the wrong thing? Okay, my apologies. I wrote the right thing, so didn't I? Is everybody cool with that? Look at what we have here, though. I should say that. I should just look at that part. You recognize that? Let me write it a different way for you then, since nobody seems to recognize it. What if I write it that way? What is that? That's f prime of 0, right? The derivative evaluated at 0. We have one little assumption here, though. What's the assumption?
It exists.
Yeah, exactly. Everybody's okay with this? Let's do a numeric example. So let's say that f of x is equal to 2 to the x. Using what we just developed, this is going to be 2 to the x times f prime of 0, right? Everybody's cool with that? So if I want to calculate f prime of 0, then can I do that limit by direct substitution? No, why not? I get an indeterminate form. I get 0 over 0, right? Okay. Is there another way I could calculate this limit?
Can you like factor 2 to 0 from the first?
I mean, you could, but you're just gonna, it's the same thing as putting a 1 times 2 to the h minus 1, which is, I mean, you could do that, it's just not helpful. Do we have other ways to evaluate limits? Yeah, you could use a graph or a table. Yeah, that's what we're talking about, just using the calculator. Right? If you can't deal with the indeterminate form via direct substitution, you still have methods available to you. x. So we'll do that. And then that. What do you think? That looks good, right? Left-hand limit is equaling the right-hand limit approximately. So we'd say that limit is about 0.693-ish. Are those okay with that? So we would say then f prime of x is 0.693 times 2 to the x. As an aside, does anybody recognize 0.693? Probably not.
Or 2 pi.
It doesn't have anything to do with pies.
Oh, okay. Just do that.
It is the natural log of 2.
I've done logs for like since sophomore year, and I still do not understand how to use them. Other than like the general, but as soon as the couple things start going on, it's
Going on like a log.
So what we'll find here is then is that that's your derivative. We'll prove this later when we talk about the chain rule. It's much easier to do it with the chain rule, but we're not ready to do that yet. What's up?
Is that just our answer?
So this was the end. I'm just pointing out that in general, that 0.693, you guys didn't recognize it. I recognized it immediately as that's the natural log of 2. And in general, this is the derivative rule for an exponential. So, Victoria.
No, I was just gonna say like would like on the top use the shortcut.
Oh yeah. Oh yeah. I'm just developing some stuff on intuition that's like, hey, this looks like the rule. Not ready to prove it yet, but that's the rule. So what if we did the same thing with the natural, or with e to the x? What's the derivative of e to the x going to be? E to the x times natural log of e. And what's the natural log of e? 1. Everybody's okay with that? So this, again, that's a theorem. You can use that the derivative of e to the x is just e to the x, which is really disappointing, right? That taking the derivative doesn't make it any less complicated. It actually makes it just the same. And then I wanted to, I think on the last multiple choice problems, one of the questions was this, when I assigned you guys the multiple choice, the last set of multiple choices. I think almost everybody got this wrong, and it's a super tough pull without what we just did there. So let's just kind of walk through this. Sound good to you guys? Sure. So that's the first thing that I'm going to do. Everybody's okay with that? I can factor out that e to the negative 1. So this is the piece that I'm going to be left to deal with. Now, how would have you been expected to deal with that without seeing what we just did? Fair question, right? You ready? This is going to be an explanation. So the first thing you needed to remember was the definition of E. Does anybody remember that from back in Algebra 2? That's... What's up, Sophia? You're okay? If you have a question, you can stop me. Okay. I just heard somebody say I'm so confused. No? Okay. I would like to help remedy that.
No,
Okay. I get that you're making, like, being self-deprecating, but...
yeah, no.
Okay.
100%.
Okay. All right. So we have that. That's the definition of E from Algebra 2. I would take the natural log of both sides. Oops. Uh-oh, can somebody let Sergio back in? Thanks. I had the door propped, and it just got too loud. Sorry, dude.
Honestly.
And what is the what's the natural log of E? That's 1. And I know that I can, if I have the limit of a composition, that's the same thing as the composition of the limits. So I can, like, push the natural log inside the limit. Everybody's okay with that? And who remembers their properties of logarithms? If I have the log of 1 plus 1 over x to the x, what can I do with that? Yeah, I can use the power property to move the exponent from inside my logarithm into a coefficient out front of my logarithm. Now things are going to get, Mr. Kulik's going to get sneaky. So I'm going to do like a change of variable here, and I'm going to replace 1 over x's with y's. Okay with that? It's okay? Get ready, because here we go again. And do another change of variable now. I'm going to say that z is going to equal 1 plus y, or the natural log of 1 plus y. What's that equivalent to saying? Use your definition of a logarithm. It's going to be the base of the logarithm to the answer equals the argument of the logarithm.
So why would you substitute y for y over x instead of just like leave it and then do z equals the log of 1 plus whatever?
I don't know, maybe because Mr. Kulik was having a bad day when he did this or something.
So there's no like, that just makes it up a little.
Yeah. I'm basically, I was trying to, this was me like sorting my way through this. I'm like, how does this have to come out to be 1? What can I do with this? And this was the notes that I wrote out for doing it. Because they don't have, I have the answer when to the multiple choice, but I don't have like how to get to the answer. So this is what I was doing, trying to use the stuff that you would conceivably had access to at that time without just like pulling some derivative definition. So this is the definition of a logarithm from way back, right? That's what I used to go from here to here. Everybody's okay with that? So what do I have here? Oh, shoot. Okay, a change here. When I change variables, that changes to y going to 0. Why is that? Look at this. What happens when x goes to infinity? Y goes to 0, right? Everybody's okay with that? Now I have to do the same thing here. If y is going to 0, what does z go to? Y going to 0, you're ending up with the log of 1, which is 0. So z should be going to 0. We need to do a little log workshop and refresh our memories on that, huh? So the so when I replace the 1 over y, I end up with 1 over e to the z minus 1. And when I replace the natural log of 1 plus y, I have a z.
Oh yeah.
Everybody's good with that? Now, I'm going to take the reciprocal of both sides. So when I take the reciprocal of 1, what do I get? And this now is almost the same thing as what I need over here, right? What's the only difference? Well, that. Does that matter, though, if h is approaching 0? Right? Negative e to the negative h goes to 1 as h approaches 0, as does e to the positive h. Correct? So it makes no difference to us. So based on the work below, that's just 1. And our answer should have been 1 over e. Woof, Mr. Kulik. That was a mess. Because I showed that this part here is equal to 1. That's what I did down here.
So you substituted 1 for that. Okay.
This result, though, is a nice one to maybe hang on to. I've seen that pop up more than once looking at AP questions where that's something that's popped up as being useful. Just like the limit as, x approaches 0 of sine of 1 over x does not exist. I see that pop up a lot. There's another one that I've seen pop up more than once when I've been looking at old AP things.
Are we gonna get like a formula sheet?
Well, we can make our formula sheet that you guys to study with, but the formula sheet on the AP exam is a blank sheet of paper.
You're kidding.
No, you got to remember everything.
They don't give us any.
Nothing.
He's like, some of these formulas when we do ACT where we can like put it in our calculator.
Like we're not.
I don't know what the calculator procedure is, but you shouldn't have anything, and I don't think you're supposed to be bringing outside materials in your calculator for the ACT or an AP exam, like your own notes.
I don't have a device.
I don't think that that's something you're supposed to do. I think if you're in, the proctors were doing their job, they would have cleared all your calculator memories.
Oh, I don't know that. Oh,
So, honestly,
I know. Hey, take a deep breath. I know.
I'm just not
I just
seeing myself
understood-
get a 5.
Oh, no, I just understood. That's what we're going
Yeah, well, no. I mean, it's gonna show off. That's the worst thing that.
Hey guys, what percentage do you suppose a 5 is?
It's it's probably like a 65,
Yeah.
but that doesn't mean I'm gonna get a
Well, I'm saying that should feel much more attainable than like, oh my God, I have to be able to get 100% or something on it, right? Like, and it's one of these things, we'll study this stuff, right? The bigger problem is going to be remembering all the rules from algebra and trigonometry than the calculus stuff that you're used to using a lot.
Not at you a single element.
I can do it all.
Besides a squared plus b squared equals c squared. Okay, well, that's what
We're going to stop here. I'm not going to continue past this. I think one section here today is probably good. I made another set of practice AP questions, just to let you know. These are going to be covering, though, the first 3 sections in totality. So, like, if you look through there would be some stuff you could do, but not everything. And does it let you go back and change answers until you finally hit submit?
Yeah.
So you could go through and try some stuff initially, or skip the stuff you're like, I don't know what to do with this. We haven't got there yet. But I have done that for you guys. Robbie?
Are those questions homework or are they just extra practice?
So these are, it's a homework assignment, but I think I have it due on the 2nd is the due date I have set for it. But I wanted to tell you that it's open if you wanted to start like picking away at things. I think there's like 15 or something of them, 20 of them. What is there? So there's 19 of them, but some of them you could do. This one you couldn't do yet. But like this one should be doable right now. This one should be doable right now. This one should be doable right now. You know, so it just kind of depends. You go through and you look. Some of them are doable right now, some of them aren't. But you could start on that if you were so inclined.
Mr. Cool, do you have any books left?
Oh yeah.
There's like literally just.
I can check one out, please, or however.
Yeah, sure. Hold on one second while I try to. There it is.